Let's continue talking about truth tables and equivalent statements in section 3-4. We're warming up by kind of reviewing what we've been doing. We're going to translate each of these 4 statements into English. So P is Romeo loves Juliet, Q is Juliet loves Romeo, and I need to do these 4 compounds. We've got a conjunction, a disjunction, and 2 negations. Remember, you can only label something as a negation if that is the only thing going on outside the parentheses. Okay, for our conjunction, we have not P and not Q. So this is, for these 2 statements, Romeo does not love Juliet and Juliet does not love Romeo. A little bit of shorthand there. Then we have not P or not Q, so Romeo doesn't love Juliet or Juliet doesn't love Romeo. Then we have the negation of. Remember, there are 2 key phrases for that negation. We're going to use one each time. Our first key phrase that we could use is, it is false that, and then we have Romeo loves Juliet, and, because that's a conjunction in the middle, Juliet loves Romeo. So there is my negation phrase. The other negation phrase that I could use is, it is not the case that. It is not the case that. And then inside parentheses, we have Romeo loves Juliet or Juliet loves Romeo. So these 2 phrases, it is false that and it is not the case that, can be used interchangeably. It doesn't matter which one you pick. Just make sure that our negations are our not statements, and the negation on the outside doesn't suddenly move inside our parentheses. We've talked about this already. We've talked about the fact that there's not true distribution with our logic statements. And we named it, I believe, De Morgan's Law. We also identified which of our statements were equivalent under De Morgan's Law. Okay. So I have gone ahead and sketched in a big multi-column truth table for our use down here. Our goal are these 4 statements that make up De Morgan's Law, to remind ourselves which pair up so that they are logically equivalent. To get there, though, I need to know P, Q, not P, and not Q. I only have 2 statements, main statements, P and Q, that I'm working with, which means I have 4 cases. If I had added R, which I'm not, I would have 8 cases. So we're going to start with our standard columns for P and Q, where P is true, true, false, false, and Q is the alternating true, false. Then I negate each of those columns. When I negate P, it flips. And when I negate Q, each of those truth values change. So now I'm looking for these 4 compound statements. I've got a conjunction, a disjunction, and 2 different negations. One negating the conjunction and one negating the disjunction. All right, let's go through each of these. For not P and not Q, I'm looking at those 2 columns. Remember, you only ever compare 2 columns at a time. So for not P and not Q, I'm looking at these columns. It's an and, so to be true, both statements have to be true. That only happens down here in case 4. Then I've got not P or not Q, still looking at these 2 columns. But now it's going to be true if at least one of the statements are true. So only the first case is false. The other 3 cases are true. All right. When I get over here to this negation, I'm looking at P and Q. I don't have a P and Q column. If you can't do this in your head, please go ahead and add a couple of columns to make this happen. I first need to figure out what P and Q would be, and then I need to negate that. Well, P and Q right here are P, Q, is only true where both of them are true. So it is P and Q are only true for this first case. But when I negate that, that first case becomes false. P and Q will be false for cases 2, 3, and 4. When I negate that, they become true. And finally, I have not P or not Q. So still looking at P or P, Q as my two columns I'm interested in. Now I've got an or, which means it will be true if I have at least one true statement. So case 1, 2, and 3 are true for P or Q. When I negate that, it becomes false, false, false. P or Q would be false for this fourth case. When I negate that, that is true. All right, we have set up our 4 cases for our 4 different compounds. The question is De Morgan's law. What do we pair up for De Morgan's law? Well, not the negation of P and Q right here. What is logically equivalent to that? The column right before it. Not P or not Q. And then we think about this final column, the negation of P or Q. Well, it is logically equivalent to this column, not P and not Q. Hopefully you remember going over this. Stop right now and look at the patterns that are formed. For our logically equivalent statements, when I think about distributing that not inside, which I'm not really distributing, but if that's what it looks like, that negation moves inside the parenthesis. When it does, it flips that symbol. Instead of and, it becomes or. Instead of or, it becomes and. That's how De Morgan's law works. Let's look at the next page. Okay, I have my 2 statements about Romeo and Juliet for P and Q. I'm told to do 3 different things. First, write the given statement symbolically. Then, use De Morgan's law to write the equivalent statement symbolically. And finally, translate that equivalent statement into English words. So A says, well, I guess this should have been 1, 2, 3 maybe. First, write the given statement symbolically. It is not the case that Romeo loves Juliet and Juliet loves Romeo. It is not the case. That's my negation phrase. Romeo loves Juliet is P, and Juliet loves Romeo, Q. That is this statement written in symbolic logic symbols. Okay, it is logically equivalent to what, according to De Morgan's law? Well, according to De Morgan's law, if I look back at that last page or if I remember my pattern, that statement is logically equivalent to not P or not Q. Well, what does not P or not Q mean in words? In words, that would be Romeo does not love Juliet, Romeo does not love Juliet, or Juliet does not love Romeo. That's what that looks like, logically equivalent in words. Okay, let's do the next one. We start with what we're given in symbols. Romeo does not love Juliet, and Juliet does not love Romeo. So Romeo does not love Juliet, that is not P, and Juliet does not love Romeo, not Q. What is that logically equivalent to? Well, if you look at De Morgan's law, that is logically equivalent to the negation of, and then I switch my symbol, P and Q. So now I need to put this in words. This would be, it is not the case that, or it is false that, either one works. Romeo loves Juliet, because that's P, or, make sure you use the right joining word, Juliet loves Romeo. There we go. Okay, example number 2. We're going to do the same thing, And then at the end, we're going to determine whether this statement is true or false. So we're adding a step. We have new statements, P and Q. P is Atlanta is a city. Q is California is a city. So I'm going to start by writing what I'm given in symbolic form. It is not the case that. That is my negation key phrase. Atlanta is a city, or California is a city. Well, I know according to De Morgan's law that that is logically equivalent to not P and not Q, because when that negation kind of distributes inside, it reverses, it flips that joining word. And so I need to put this into words. When I put that into words, I would say Atlanta is not a city, so that's not P. Atlanta is not a city. And California is not a city, because I have not P and not Q. Now I need to determine if the statement is true or false. Atlanta is not a city. That's false. And, conjunction, California is not a city. That's true. California is a state, not a city. What is the truth value of this? Well, if it's a conjunction, to be true, both parts have to be true. They're not both true. Therefore, and my little triangle of dots means therefore, this is a false statement. If this is a false statement, then that was also a false statement. Sometimes if we reword things, it makes it easier to understand what's going on. Okay, let's look at the next one. Let's look at part B. We're using our same values for P and Q. We've got Atlanta is not a city, so that's not P, or not Q. California is not a city. We've got an or here. And then we go to De Morgan's law and say, okay, well, that is the same thing as saying, that is logically equivalent to the negation of P and Q, where that flips. So I'm going to put this into words. It is not the case that, or it is false that. And then P, Atlanta is a city. Let's capitalize Atlanta. Atlanta is a city, and California is a city. That is Q. Okay, let's look at the truth value. It is false that. So I'm going to be negating whatever's going on in here. Atlanta is a city is true, and California is a city is false. So the truth value of this, T and F, that is false, correct? That is false. That compound is not a true compound. That conjunction is false. But I need to negate that. If I negate that, the truth value changes, and therefore what I'm saying is true. So we're dealing with some convoluted statements, some statements that kind of mess us around. We're applying the De Morgan's law to put that in other words to help us try to figure out whether what we're being told is true or false. Okay, equivalent conditional statements. We worked on this too. This is kind of a review about equivalent conditional statements. It says to place each symbolic statement next to the correct term. We have the original conditional statement, which is just if P then Q. Now, do you remember how I told you to kind of remember these? What I said was, let's say in means not. So when I apply not to both of those, not P, then not Q, that's my inverse. My contrapositive is where I mess it up as much as possible. So I rearrange the two and I negate both of them. So this one would be not Q, then not P, which means the converse is the remaining one. The converse is going to be where I just switch places. So I've got if Q, then P. Now we are given the truth tables already built for us. We've got our conditional truth table, if P, then Q. Then what about this one? If Q, then P, we said that is the converse. Not P, if not P, then not Q, we said is the inverse. So we've got this one, this one. And finally, not Q, if not Q, then not P is my contrapositive. And we need to look to see how these pair up so that they are logically equivalent. Well, if you compare the truth values for that last column, you see that the conditional is logically equivalent to the contrapositive, and the converse is logically equivalent to the inverse. So my original conditional statement is logically equivalent to the contrapositive, and the inverse is logically equivalent to the converse. Okay, let's do this. Next page, example 3. Now, I didn't write this because I'm not a huge fan of calzones, but they're fine. I'm told that if the menu includes calzones, then I break my diet. This is a conditional statement because it's if-then. For this statement, P would be the menu includes calzones. And Q would be I break my diet. Okay, we're told to write the converse. Well, think about what the converse is. Remember the logically equivalent statements I just did? My converse is when I switch the order. So the converse would be if Q, then P. If Q, then P would be if I break my diet, then the menu includes calzones. The inverse is when I take the original conditional, if P then Q, when I take that original conditional and I negate both pieces. Not Q, then not P. So that would say, if the menu does not include calzones, then I don't break my diet. And finally, the contrapositive. My contrapositive is where I mix it up as much as possible. So I say not if not Q, then not P. So if I don't break my diet, then the menu does not include calzones. Now, it doesn't ask this, but I'm going to ask, which of these statements mean the same thing? Well, the converse and the inverse are saying the same thing. No matter which way I say it, if I break my diet, then the menu includes calzones. Or if the menu does not include calzones, then I don't break my diet. Those mean the same thing. They're logically equivalent. A and D are also logically equivalent. If the menu includes calzones, then I break my diet means the same thing as if I don't break my diet, then the menu does not include calzones. Okay, example 4. If I'm in Houston, then I'm in Texas is my conditional statement. If P, then Q. Well, if that's my conditional statement, that means P is I am in Houston, and Q is I am in Texas. Okay? Write the 3 statements that go along with that conditional statement: the converse, the inverse, and the contrapositive. Remember that converse is if Q, then P. Inverse is not if not P, then not Q. And contrapositive is if not Q, then not P. Well, if Q, then P would be if I'm in Texas, then I am in Houston. C would be, the inverse would be, if I am not in Houston, then I am not in Texas. And D, the contrapositive, would be if I'm not in Texas, then I'm not in Houston. Okay, I want us to take a second and think about the truth values of these statements. Remember that, again, conditional and contrapositive are logically equivalent, and then converse and inverse are supposed to be logically equivalent. And let's go back and read these and see if that matches up to what we think. All right, if I'm in Houston, then I'm in Texas. Well, Houston is a city in Texas, so that's true, because if I'm in Houston, then by default, I'm in Texas. B, the converse, that's my conditional. Converse says, if I'm in Texas, then I'm in Houston. Well, that's not true, because I'm in Texas, I'm in Fort Worth, but I'm not in Houston. So that's a lie, that's false. C says, if I'm not in Houston, then I'm not in Texas. Well, I'm not in Houston, but I am in Texas. So that's false. And finally, if I'm not in Texas, then I'm not in Houston. Well, if I'm not in the state of Texas, then I can't be in the city of Houston because Houston is in Texas. So there you have it. My conditional and my contrapositive have the same truth value. My converse and my inverse have the same truth value. Okay. Let's look at the next page, example 5. Same thing. If the sun is shining, then I'm outside. Oh, except we don't have to write words with these. We just write symbols for the most part. If the sun is shining, then I'm outside. So that's my if statement. If P, then Q. That's my conditional. Where the sun is shining is P. I'm outside is Q. And it asks you to write the statement and then say what it is. Write the statement and say what it is. I'm going to pause the video. I'm going to answer B through G, and then I'll come back. So you pause your video and answer yours. Okay, so there are each of these words in symbols, and I identify which rearrangement of the conditional statement it represents. Example 6, we're doing about the same thing. Example 6 wraps around to the next page. So go ahead and pause the video knowing that this is my conditional statement. Fill in all the parts for example 6, A through D, and then restart the video. All right, here we go. So for example 6, statement P, the fruit is a lemon. Statement Q, the fruit is yellow. When I'm given, if the fruit is yellow, then the fruit is a lemon, I've rearranged my statement so I have if Q, then P. This is the converse of my original conditional statement, and it is not logically equivalent to the original statement, that conditional statement. Let's look at C. The words in C, if the fruit is yellow, not yellow, then it's not a lemon. If not Q, then not P. Is the contrapositive of our conditional statement, and yes, it is logically equivalent to what I started with. And finally on D, I have if not P, then not Q, which is the inverse of my conditional statement, and no, it is not logically equivalent to the conditional statement. We have another example. We have example 7 before we move on to some practice. I'm going to pause it again, fill mine in, so you do the same. All right, example 7. From our conditional statement where P is I'm in Tulsa. Tulsa is a town, a city in Oklahoma, in case you didn't know. I'm in Tornado Alley, which is what we call this area of the Southwest that just gets those frequent spring tornadoes. B, if I'm in Tornado Alley, then I'm in Tulsa. That is my converse, if Q, then P. D, if I'm not in Tornado Alley, then I'm not in Tulsa, is if not Q, then not P. That's the contrapositive, and saying this is logically equivalent to my conditional statement. If I'm in Tulsa, then I'm in Tornado Alley is true. If I'm not in Tornado Alley, then I'm not in Tulsa because Tulsa is in Tornado Alley. So that's also true. If I'm in Tornado Alley, then I'm in Tulsa. Well, not necessarily, because we're still in Tornado Alley and we're not in Tulsa right now. And then finally, I have my inverse, if not P, then not Q. If I'm not in Tulsa, then I'm not in Tornado Alley. Not necessarily true. Okay, not true, not logically equivalent. So these two are false. Inverse and converse are false in this case. Contrapositive and conditional are true in this case, in this example. Okay, we have our practice statements here. I am not going to talk all the way through it. I'm going to pause my video. I'm going to fill it in, and I want you to do the same. I want you to see what you can do on your own, and then we'll look back at them to see how you did. We start at the top of the page by reviewing De Morgan's laws, making sure you know how they pair up to logically equivalent statements. That's what this double-sided fancy arrow means, is that they are logically equivalent. Then I took each of my given statements on example 1, rewrote them in symbolic form, and applied De Morgan's law to determine which two were logically equivalent. Example 2, I'm applying De Morgan's law as well. First, writing the statement in symbolic form, seeing what that symbolic form is logically equivalent to according to De Morgan's law, and then rewriting the equivalent statement. So I'm also asked to determine if each statement is true. This pair of statements, the one I was given and the one I rewrote, will have the same truth value. Let's just look at one of them. If I look at not P and not Q, well, not P, it is not the case that Bart Simpson is a cartoon character. That's false, because Bart Simpson is a cartoon character. It is not the case that Dr. Meredith Grey is, let's do it this way. Bart Simpson is not a cartoon character is false. Dr. Meredith Grey is not a cartoon character. That's true. She's not. She's a doctor. She plays the doctor on TV, at least. So conjunction, F and T, false and true. Conjunctions, both statements have to be true. So this pair of statements is false. On B, I've written the logical symbols for what I was given. Using De Morgan's law, I've said that is logically equivalent to not P or not Q, and then I put that into words. Well, not P we determined was false up here. Not Q we determined is true. This time, though, it's a disjunction, and if one statement is true in a disjunction, then the disjunction is true, so both of these statements are true. Bart Simpson isn't a cartoon, or Dr. Meredith Grey isn't a cartoon. That's true, because she's not. C and D work the same way. I've written my original statement in symbols, used De Morgan's law to get the logical equivalent, and then put that into words. Both of these pairs of statements, as I'm given, are false. Make sure that you're able to go through and show why. Do the back side. Pause the video, do the back side, and then come back. On the other side, we talked about logically equivalent forms of conjunctions and disjunctions with negations using De Morgan's laws. Now we're talking about logically equivalent forms of conditional statements using the conditional, contrapositive, converse, and inverse. Hopefully you have this by now. Our example on example 3 encourages you to symbolically identify which one we have and then show which are logically equivalent pairs. And finally, we're showing an alternate way to say the same thing. If you go to school, then you study means the same thing as if you don't study, then you don't go to school, because they are logically equivalent. If you study, then you go to school means the same thing as if you don't go to school, then you don't study, because they are logically equivalent. We're using those conditional, contrapositive, converse, and inverse equivalencies.